Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. Welcome back to SID2004. We're going to continue our lecture. So on Tuesday, we've touched a little bit on the Merrifield resin, okay, on the synthesis of peptide on the solid support or solid phase peptide synthesis. Okay, so we stop here on Tuesday. So just continue until the remaining of the lecture. Okay, and then afterwards I'll put in more kind of like practice tutorial for you guys to have a practice based on this lecture and the previous lectures. Okay, all right. So just focusing on the SPPS, solid phase peptide synthesis. So say, for example, you want to synthesize this tetrapeptide again, GKAG. Okay, so how do you synthesize it? Is first off, as I mentioned, I'm not sure why this is broken. So you have your first amino acid at the C terminal. Okay, and first off, you have the Merrifield resin. Okay, so that is the Merrifield. So the whole thing is called as Merrifield resin. So this entity over here is the polystyrene, and while in the middle there we have a molecule that we call as a linker. Okay, so a linker is because of polystyrene. If you look at the structure, it does not have a functionalized functional group. Okay, so you need to functionalize it, otherwise the carboxyl functional group, which is less reactive, will not be able to be linked to the solid support. Okay, so when you have it like this, okay, so originally, if you remember, it's a chloride over there. So you can now use the chloride as a leaving group and form an ester bond for your first amino acid over there, and then you can grow it from C to N. Okay, so how do you actually synthesize it stepwise? So I will show you here as one of the example of an orthogonal chemistry called BOC, TBU-SPPS. Okay, the peptide that we synthesize will be the same: glycine, lysine, alanine, and glycine again. And something that you need to remember is the square represents the amino acid itself, and the circle represents the BOC protecting group. Okay, so we start off with a Merrifield resin. How do you do that? So the first step is to do a coupling from the C terminal, the carboxyl terminal of the amino acid, because the N terminal is now protected with POC. Okay, so the C terminal amino acid is attached to the solid support by means of SN2 reaction. So its carbonyl group attack a benzyl carbon of the resin, displacing the chloride. Okay, so it's a simple reaction as that, doing that, and then chloride will leave as a leaving group. Okay, so by doing this, you manage to couple the first amino acid. So the second step, so once you have the amino acid coupled, of course you want to add in additional amino acid. So what you do is to remove the BOC protecting group using acid, strong acid, trifluoroacetic acid. As I previously mentioned, the BOC protecting group is acid labile. Okay, so you use TFA, you can either use neat or 100%, or you can dilute it in 50% TFA in DCM. So why do you need to dilute it? Well, of course, when you do a reaction towards the end of the day, you need to consider how the industry will adapt the reaction. Okay, and industrial is always capitalism. Capitalism is always about money. So similarly, what we see here is that because DCM is a widely used solvent, so it is cheaper than TFA. Okay, TFA is a fluoride. You need to have, instead of just using an acetic acid, which is not that acidic, so you need to actually transform into a trifluoroacetic acid, and therefore it becomes a very, very strong acid, and thus is more expensive than just simply a DCM. However, a 50% TFA in DCM works as well as a neat TFA, so it can cleave off the BOC. Okay, very, very easy. Now you might ask me, but what I've seen here, doctor, is just an ester group, or wouldn't the ester deprotonate as well, or will not will it not be cleaving that particular bond as well? The answer is yes, you are true, you are correct. So if you use TFA, you put everything in there, okay, so you will get that bond also cleave off on top of that bond. Okay, so how do you overcome this? You overcome this by limiting the time by which the reaction or the solid support, the peptide on the solid support encounter the TFA. Okay, so because bulk, so this reaction is way faster than this. Okay, so this one is way faster, this one is slower. So what we do in the lab is we expose to TFA in a very short duration. Okay, a very short duration. So how do you do that? So normally in one reaction you leave it for about, sometimes 1 hour, 2 hours, 3 hours, and so on and so forth, sometimes days. But for this reaction, you just expose the peptide within 1 minute. Okay, so you normally just do it 1 minute twice, or you just do it 1 to 2 minutes single. Okay, because bulk reaction is always active. So if you do something like this, what will happen is that you will remove the bulk at 100% efficiency, or, well, since I said no reaction is 100% accurate, so we'll just call it 99% over here. Okay, so you will be able to remove 99% of the bulk within this time frame, while this reaction over here, the hydrolysis, under the same condition, under the same time, it's less than 1%. Okay, so now you still be able to have your peptide link to the solid support. Okay, so once you deprotect the bulk, what you do next is, as we've covered, you use a reagent to activate the carboxyl group. Okay, carboxyl group of incoming amino acid, not the ones that already coupled to the resin. So the second amino acid. So you activate it using a reagent, and of course you need to have a base. And why you need to have a base? Because once you deprotect this, okay, because again you use acid, right? So you will definitely protonate the amino terminal. So if it's protonated, it will not be reactive. Okay, so the base is needed in this case is to deprotonate or neutralize the amine, okay, amine plus, or so deprotonate. Okay, so deprotonate the positive amine, and therefore an incoming activated amino acid can now be reactive enough, for this to react over to the carbonyl group, and thus forming your dipeptide. Okay, so that is the third steps, third and fourth step. So you mix it, it's the fourth step. And what you do after is you just repeat the cycle until you finish your sequence. So it's very easy, and it's very, very quick, so to say, as compared to solution phase synthesis. Okay, because now, as you can see here, I did not put any purification step, because the purification step is as easy as draining the solution. As I shown previously, you have your vessel. Okay, you have your filter, you have your solid support over here that cannot pass through the filter, and then you just add in solvent to just wash the resin, and the solvent will go out with all the byproducts and the bases and unreacted amino acids. Okay, so you can pretty much clear out, remove everything, and get a clear or a clean solid support, and thus you can just repeat the cycle, add in more amino acid, do the step again, rinse it, washing it, and you can grow the peptide very, very easily. Okay, so protein is synthesized from C terminal to N terminal. So that one is the C terminal over there, and then that one is the N terminal. Okay, C to N. Right. So because the synthesis is repeatable, the technique can easily be automated. Okay, because there's only like 4 steps, so to say. Okay, again 1 2 3 4 1 2 3 4. So you can automate it very, very easily, and I will show you an equipment that does that in the next few minutes. Okay, in contrast, in biology, the protein is synthesized from N to C, and of course it's not spontaneous. Again, it never be spontaneous, but in biology we do have our own machinery to do this, and that machinery is what we call as the ribosome. Okay, so you have the ribosome as the machinery, and for each amino acid you have your own activating agent. Okay, you have multiple things. So even in our nature, in our body, so we do need to have something else. We do not simply just put into amino acids and it will spontaneously form a peptide. Okay, so yep. All right, and then finally for the chemistry bit, once you have all your peptides sequence completed, so the final step is to remove the peptide off the solid support, and you want to remove all protecting group. And in the first generation Merrifield resin, you do this by treatment of hydrogen fluoride. Okay, and I put it here under controlled condition. Why? Because hydrogen fluoride, if you look at the safety feature of this, okay, it's not hydifluoride, but it's hydrogen fluoride. It has no smell. Okay, in contrast to some acid, for example, tetroacetic acid or acetic acid, so to say, there is a smell, right? So, but HF has no smell. So if you actually work with HF and you accidentally breathe it in, there's no smell. So you don't know whether you actually smelled it, but what you will know is that you will feel that your chest is burning. Okay, so burning sensation is part of the symptoms of HF exposure. Okay, so to do this, you need to have a very, very controlled condition. But unfortunately, in chemistry, for now, we do not have that facility available. So the Merrifield approach of peptide synthesis is not suitable to do it in our chemistry building or chemistry department, so to say. But I will show you an alternative to do peptide synthesis, and that is the alternative that I'm using for my research. Okay. All right. So moving back to the final step. So when you use HF, because it's a very, very strong acid, it will remove the Boc protecting group on the N terminal. It will remove the T-butyl group protecting all the side chain, and of course you'll be able to cleave the peptide of the linker from the resin and therefore get a crude peptide as shown here. Okay, so this one is a crude. All right, so now since I mentioned that HF, we do have a HF facility in the chemistry department. So the orthogonal chemistry of Boc and T-Boc or T-butyl is not being utilized. So what I utilize instead is what we call as FMOC and Boc. So FMOC Boc orthogonal chemistry. So what are the differences is that, so you have your amine group over there. So instead of having a Boc over this particular site, what we have now is FMOC. Okay, so why FMOC? Because FMOC is basic labile, while Boc is acid labile. So they are like compatible to one another. So say for example, if you have a lysine, 1 2 3 4 5, okay, and H2. So what you will have over here, over the protecting group on the gamma lysine, is you will have a Boc. Okay, so and and this is your amino acid lah. Okay, and why do you combine these two together? Is because if you want to remove FMOC, which is the basic labile, you use piperidine, but the bulk stays because the bulk is base resistant or acid labile. So if you use a base, it does nothing to the bulk. Similarly, if say for example you have your peptide over here with a lysine at the end, and you want to do a modification on the side chain of the lysine, then yes, you can do that by removing the bulk but keeping the FMOC intact using an acid, and then you can further modify at the side chain only. Okay, so that's one of the options. So this is the option that we have and that is readily available to use in my lab at the chemistry department. Okay, so this is just to show you the general protocols for F1 chemistry. Yeah, pretty much the steps are identical to the box synthesis. It's just that you are substituting TFA with piperidine. Okay, so you can just read it on your own. So what are the advantages? So I've talked about what SPPS are. Well, technically I've also touched about the advantages, but this is just to point out to you that there are clear advantages of SPPS compared to SPS. So number one, it's quick and seamless. What I mean by seamless is that you have everything in one vessel. Okay, you do not need to do anything until you complete the whole synthesis. Then you just take out the resin and then follow through with cleaving the resin off the solid support, then you get your peptide. So it's very easy. So in contrast, if you were to do
solution phase synthesis,
you need to move the reaction vessels back and forth between the reaction condition and the rotary evaporator at least. But if you were to do a column chromatography, then you need to take out your solution, put it into a column, purify that, and then collect the elute product back into a reaction vessels and so on and so forth. So it's very seamless. Second one is you can automate it very easily as compared to solid support, solution phase synthesis. Yes, you can still automate it, but then the automation needs to include evaporation, which will take time. Therefore, a solid support
synthesis,
is a faster way of the two. Okay, and an example of automation is being shown in these two pictures over here. Okay, so this is what we call as the name of the equipment is a Symphony Peptide Synthesizer. It says here Protein Technologies Incorporated. So that's the company that produces this. So this equipment costs roughly about 100,000 USD. Okay, roughly. If you were to bring it back into Malaysia, then probably the middleman will charge you about 600,000 to even 1 million. Okay, ringgit. So it's very expensive. So far I have not seen this equipment in Malaysia at all. I've used it once, not once, multiple times during my stay back in Australia. Okay, so just to talk about this machine a little bit, if you were to do a solution phase or a solid phase synthesis manually without a machine, you normally will just do like one reaction at a time. But this machine, because it's automated, can actually have 12 different vessels. So these are all individual reaction vessels, and the system can you can actually set the system so that vessel number 1 and number 2 and number 3 until number 12 have a different sequence of amino acid altogether. Okay, so it saves you a lot of time. So if you consider that one peptide will take you 2 days, if you, well, it doesn't, 2 weeks is more feasible. Okay, if one peptide takes you 2 weeks to synthesize, if you have 12 peptides, then you will need about 24 weeks to complete. Okay, but imagine this machine, 12 peptides, because it can run simultaneously. It will take you just 2 days. Okay, so it saves a lot of time. Um, Additionally, what you see on the right hand side over here is an alternative machine, but this one only has two reaction vessels, and this one is cheaper, at costing about what was it, if I'm not mistaken, about 20,000 USD. Okay, so it's way cheaper than the one over here, right? And the beauty of this machine is that you can synthesize more than 100 amino acids in less than a week with no issues. If you were to do it manually, then it will take a longer time. During my first training, when I was first the first peptide that I synthesized only has a 30 amino acid. It took me 1 month to actually complete the whole thing. Okay, so that's the beauty of using an automatic system. All right, but of course there are some limitation. SPPS cannot be compared to how nature works. Okay, in nature, in our body, for example, everybody of us, we manage to produce thousands of peptides. Well, uh, synthesized peptide containing thousands of amino acids in seconds. Okay, and simultaneously synthesize thousands of different proteins with no mistakes. So, our body is the best machinery. It's an automatic system because we don't do anything. Okay, it will just do it on its own. So that's the beauty and that's the limitation of the SPPS. Protein complexity is different, but different protein will require post-synthesis approach to ensure its function. So this is for going back to a synthesis. So if you were to synthesize using SPPS, the same method might not work in all proteins. Okay, so as an example, so this is the one of the work that I've completed back in Australia. Okay, see, it was published in 2018, about 3 years ago, and we are currently publishing the other one, the most updated version. Um, Hopefully, it will get accepted soon. Okay, but as we've learned previously, you synthesize from C to N. Okay, that's the best option, or you can also do it N to C. Now, a peptide like this, which is a unique form. Okay, where is the N? Where is the C? You do not know. Okay, so these are some of the because it doesn't have an end, so everything is connected. So imagine if you have that type of synthesis. Okay, so there's no start, there's no end, but where do you start? How do you do it? Okay, so these are some of the complexity of peptide synthesis. The theory that you guys learn is just a straightforward synthesis. I did not even touch about what modifications that you can do on your R group. So yep, I think pretty much that's about it. This is just to show you one of the work that I've done. My field is actually in peptide chemistry, so that's why I'm teaching you peptide chemistry in more detail. All right, so finally, help me by doing this survey. Okay, I will add into the tutorial questions following this slide and some resources. That is all from me. Thank you, and see you guys on next week. Take care.